Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from the University of Jammu. Today we are going to discuss about a module entitled Classification of Crystalline Solids under the paper Crystallography and Crystal Growth. Learning objectives. In this module, we will learn about the binding forces that hold a crystal together. Solids are classified according to the type of bonding in them. Ionic, covalent, metallic, molecular, and hydrogen bonded crystals are described. Characteristic features of various crystal types are given. Various types of bonds, namely ionic bond, covalent bond, metallic bond, molecular bond, and hydrogen bond are discussed, providing understanding of how crystalline solids are held together. Interacting forces contributing to the lattice energy of crystals are explained. Expression leading to determination of lattice energy of ionic crystals is derived. Calculation of repulsive exponent from the compressibility data is explained. Now, classification of crystalline solids. The definition of a crystal in its simple form is that a crystal is a solid with naturally occurring plane faces. It has already been explained that the external morphology of a crystal is a reflection of the regularity of the internal arrangement of the atoms or molecules within it, which one can easily confirm by the use of X-rays. So, the definition of a crystal can be extended by including any solid material which has the atoms, molecules, or ions of which it is made in some regular order. We shall consider here the various types of bonds which exist in crystals and hold them together. The classification into bonds of different kinds is done for simplicity of description, but in practice, the bonds in a real crystal may be a mixture of two or more of these types. What are the binding forces that hold a crystal together? The answer to this question lies in describing the types of binding forces and how, in terms of these forces, the solids can be classified. Types of binding. The attractive force increases as the distance between the atoms decreases till a limit is reached, and beyond which short-range repulsive force between the like charges of nuclei comes into play. Depending on the binding energy, solids are classified into 5 groups. By and large, the important differences among the crystal types of crystal bonds may be attributed to qualitative differences in the distribution of electrons around the atoms and molecules, or on the distribution of outer electrons in space. Based on the type of binding, the solids are classified as given here. Ionic crystal. The examples are NaCl, LiF, Kf, MgO, etc. B. Covalent crystals. Examples are diamond, silicon carbide, germanium, etc. Metallic crystals. Examples are copper, silver, sodium, and iron. Molecular crystal. Examples are argon, methane, and then hydrogen bonded crystal. Examples are water, that's ice, and HF. Now let us explain what essentially we mean by binding energy. Binding energy is the energy necessary to dissociate the solid into separate atoms, molecules, or ions as may be applicable. It is taken at room temperature, except for the molecular crystals where it is taken at the melting point. The binding energy is expressed either in kilocalories per mole or in electron volt per molecule. It may be noted that 1 electron volt per molecule is equal to 23.05 kilocalories per mole. The ionic, covalent, and metallic bonds are regarded as strong or primary bonds, and the hydrogen and molecular bonds as the weak or secondary bonds. Provides classification of crystal types in the form of a table, which gives crystal type, the examples, the binding energy, and the characteristics. The crystal type, if it falls under ionic type, the examples of this are sodium chloride. The binding energy in terms of K calories per mole is 180. The characteristics are strong infrared absorption, low electrical conductivity at low temperatures, good ionic conductivity at high temperatures, good cleavage, formed by a combination of highly electropositive and highly electronegative elements. In this class also falls lithium fluoride, which has the same characteristics as said before. However, the binding energy in terms of kilocalories per mole is 240. Now the second type is the covalent bond. In this there are three crystals. Example given here: diamond, silicon carbide, and germanium. Diamond has binding energy of the order of 170 in kilocalories per mole. Silicon carbide has 283. For germanium, it's not known. The characteristics are poor cleavage, poor thermal conductivity, high hardness, low electrical conductivity at low temperatures, formed by a combination of the higher elements in the middle column of the periodic table. The third is metallic bond. Examples are sodium and iron. For sodium, the binding energy is 26 kcals per mole, and for iron, it is 94 kcals per mole. They have the characteristics like opaqueness, ductility, malleability, high electrical and thermal conductivity, and are formed as a result of combination of atoms of electropositive elements. The fourth crystal type is molecular. The examples are methane, that is CH4, and argon. For methane, the binding energy is 2.4 kilocalories per mole, and for argon, it is 1.8 kilocalorie per mole. The characteristics are compressible, generally evaporate as stable molecules. They have low boiling and melting points. They are formed by inactive atoms such as the rare gases and saturated molecules such as hydrogen and methane. Fifth crystal type is hydrogen bonded. Its examples are ice, that's H2O, and hydrofluoric acid, that's HF. For ice, the binding energy in terms of kcals per mole is 12, and for hydrofluoric acid it is 7. The characteristics of this type of crystal type is tendency to form groups of many molecules. That is a process known as polymerization, and higher cohesive energy of molecules as compared to similar molecules without hydrogen bonds. Bonding in solids. Ionic bond. The existence of ions in aqueous solutions is a reality which is commonly an acceptable explanation of electrolysis and of the conductivity of a salt in solution or in a molten state. When a simple salt, say for example sodium chloride, is dissolved in water, the heat of solution is relatively small. This heat of solution is much smaller than would be expected if the salt consisted of molecules which had to be broken up into ions as it went into solution. It indicates that the salt may not really contain molecules at all but is already ionized even while it is a solid. Several simple salts occur as ionic crystals, that is, there are no definite molecules, but there is a collection of positive ions and a collection of negative ions, each positive ion being surrounded by negative ions and each negative ion being surrounded by positive ions. Bonding in solids. The whole structure is electrically neutral, there being an attraction between ions with opposite charges and there being a repulsion between ions with charges of the same sign. The equilibrium of the crystal is maintained as a result of balance between these two effects. However, it is an established fact of electrostatics that a system of stationary charges cannot be in equilibrium under their own electrostatic Coulomb forces of attraction and repulsion. It is known as Earnshaw's theorem. If the electrostatic forces were the only forces in action, then all the charges would be attracted to those of opposite sign and the whole solid would collapse to occupy zero volume, if it is assumed that the ions are just point charges and do not possess size of their own. Let us take sodium ion as an example. It has a nucleus of finite size, approximately of the order of 10 raised to minus 12 centimeter in radius, carrying charge of plus 11 units, and it is surrounded by 10 electrons, thus giving a net positive charge of plus 1 unit for the ion. Application of Bohr's atomic theory. These electrons are in orbits of radius of the order of 10 raised to minus 8 centimeter. For example, the radius of the 1s electron's orbit in a hydrogen atom is of the order of 0.53 into 10 raised to minus 8 centimeter, which is the Bohr's radius. Quantum mechanical or wave mechanical treatment would say that each electron in the atom is described by a wave function, which is found by finding the solution of Schrödinger equation, and that a simple way of visualizing is to consider that the electrons exist as clouds of negative charge around the nucleus. Now, applying this logic, we may suppose that if two atoms are brought closer enough, then these charge clouds will get in the way of each other and will eventually result into a repulsion between the two atoms. This phenomenon persists in the case of ions, and there will be repulsion between the charge clouds of the outer electrons of two ions at small distances apart. This is quite independent of the electrostatic force between the ions due to their actual net charges. So, if the result of the net charges on various ions of an ionic structure is to create force of attraction between the ions, this force of repulsion between the charge clouds is required to counter, balance the attraction and maintain the ions apart. The quantitative assessment of the two contributions to the forces between the ions in an ionic crystal is dealt with further in the lecture. The forces which bind the atoms together in ionic crystals arise out of electrostatic attraction between positive and negative ions. In ionic crystals, electrons are transferred from atoms of one type to atoms of second type, so that the crystalline solid is made up of positive and negative ions. The ions arrange themselves so that the Coulomb attraction between ions of opposite sign is stronger than the Coulomb repulsion between ions of the same sign. The ionic bond is thus essentially the bond resulting from the electrostatic interaction of oppositely charged ions. Let us understand ionic bond more closely. An ion, being a charged atom, has a stable electronic configuration like that of an inert gas. The neutral attains this configuration either by accepting or donating an electron, as for example Li plus, Cl negative, and so on. The charge distribution of such ion is spherically symmetrical, that is, the interaction of the ion with other ions is independent of direction. The ionic bond thus is due to Coulomb attraction between two spherically symmetrical charges of opposite sign. NaCl is a typical example of ionic crystal in which an ionic bond is formed by mutual attraction of two heteropolar ions Na plus and Cl negative, as is shown in the figure, having the following electronic configuration. Na has 1s2, 2s2, 2p6, 3s, and Cl has 1s2, 2s2, 2p6, 3s2, 3p5. Na plus, which has 1s2, 2s2, 2p6 configuration, is a neon configuration. Cl negative 1s2, 2s2, 2p6, 3s2, 3p6 is like argon configuration. Ionic crystals are characterized by strength, hardness, etc., as mentioned in the table. Generally, the ionic bond is non-directional, but there are cases where the ions deviate from the above picture of spherical symmetry and the bond is rather directional in nature. It is well known that the salts produced by combining highly electropositive metals and highly electronegative elements such as the halogens, oxygen, and sulfur are the ideal ionic crystals. Other more complex salts such as metal carbonates and nitrates and ammonium halides also may be classified as ionic crystals. Most ideal ionic salts are diamagnetic, the exceptions being salts of transition metals, which generally are paramagnetic and sometimes are ferromagnetic. The halides and oxides of the similar metals generally have an electrolytic conductivity which increases as the temperature rises. It has been shown that the high temperature conductivity sigma satisfies the relation sigma equal to A into e raised to power minus alpha by T, where capital A and alpha are practically constant. Covalent bonds. The name covalent bond, also known as electron pair or homopolar bond, was first introduced by Langmuir in 1919. This bond is formed between two atoms by sharing a pair of electrons or pairing two unpaired electrons of two atoms thus bonded. An atom is relatively more stable when the outer shell has full quota of electrons. In ionic bond, the participating atoms attain stable configuration by transference of an electron from one to the other, whereas in covalent bond, the stability is attained by sharing of the electrons. Let us take the example of Crystalline molecule, that is Cl2. The electronic configuration of neutral Cl is 1s2, 2s2, 2p6, 3s2, 3p5. Here, Cl atom having 7 electrons with the configuration 3s2, 3p5 in its outer shell will require one more electron to satisfy the stability requirement. This can be achieved when the two chlorine atoms share one pair of electrons between themselves, as shown in a schematic diagram of the figure. In this process, they acquire the closed shell configuration, that is 3s2 3p6 type of orgon. It is worth noting here that only two electrons having some orbital quantum numbers, e.g., total quantum number small n, azimuthal quantum number L, and magnetic quantum number M, but opposite or antiparallel spin S can pair up. Here, chlorine atom has only one unpaired electron, and it can effectively pair up with the unpaired electron of another chlorine atom to form a single covalent bond. The number of such bonds in an atom depends on the number of unpaired electrons. The charge distribution in this case is not spherically symmetrical. The covalent bond has directional properties and may be visualized as the overlapping of electron cloud of two atoms, as is shown in the above figure. According to suggestion of Pauling and Slater, the strength of the bond is greatest when there is maximum overlapping. The covalent crystals have characteristic properties as given in the above table. It should be noted that atoms which are close to the inert gas configuration tend to be ionic, but those far away from the inert gases in the periodic table have a tendency to be covalent. Ideal valence or covalent crystals are monatomic, non-conducting substances which have high cohesive energies and high value of hardness. Diamond is the prototype of this class, just in the same way as the alkali halides are the prototype of ionic crystals. Diamond structure has the characteristic feature of having 4 number of nearest neighbors of each atom, which is equal to the ordinary valence of carbon. The covalent bond is the normal electron pair bond of chemistry encountered particularly in organic chemistry. It is characterized by high density of electrons between the ions and also by marked directional properties. The carbon bond is a familiar example of the directional properties of the covalent bond. Carbon atoms quite often prefer to join onto each other or to other atoms by 4 bonds making tetrahedral angles with each other. It means that each carbon atom will be at the center of the tetrahedron formed by the nearest neighbor atoms. Diamond and methane are typical examples of the tetrahedral covalent bond. The diamond structure is loosely packed in a geometrical sense. In this case, the structure would require 12 nearest neighbor atoms. The covalent bond is believed to be usually formed from 2 electrons, one from each atom participating in the bond. The spins of the 2 electrons in the bond are antiparallel. The carbon atom with configuration 2s2 2p2 has a tendency, in a way, to fill up the 2p6 electron shell by sharing electrons with 4 neighbors. There appears to be a continuous range of crystals between the ionic and the covalent limits. It is both interesting and important to estimate the extent to which a given bond is ionic or covalent. It appears to be difficult to do so with certainty. One may take NaF as an ionic crystal and think possibility of INSB as largely covalent, but it is difficult to talk about the nature of the bonding of ZnS or PbS. However, Pauling's semi-empirical formula suggests that atoms with nearly filled shells, Na and Cl, tend to be ionic, whereas atoms not close in the periodic table to the inert gases tend to be covalent, as for example C, Ge, Si, Te. Let us try to understand formation of covalent bond in terms of wave mechanics. This bond is formed when two atoms each contribute one electron to form an electron pair, which is then shared by these two atoms, and in some way this electron pair manages to form a bond which holds the two atoms together. According to Bohr's theory of the atom, or the old quantum theory, electrons within an atom are arranged into shells, and the atoms tend to acquire complete shells of electrons if possible. We have already described the case of Na and Cl as shown in figure 22.1. By losing its outer electron, the Na atom requires a complete outer shell of electrons by donating this electron to the Cl atom, which then acquires a complete outer shell of electrons. This way both Na and Cl are satisfied and acquire complete outer shells, thereby becoming ions. Covalent bonds result in case of atoms would have to lose a rather large number of electrons if they were to acquire a complete shell of electrons. Carbon atom is one such atom which finds it more convenient to share its 4 outer electrons with 4 electrons from other atoms than to form a carbon ion. So it forms 4 covalent bonds with other atoms. The Bohr theory is silent about how the sharing of electrons takes place. It is therefore necessary to know if more modern version of quantum theory or wave mechanics can provide satisfactory explanation of this. According to wave mechanics, an electron in an atom has associated with it a wave function psi, which depends on the position of the electron and on time. This wave function psi is determined by solving Schrödinger equation or wave equation for the atom in which the electron happens to find itself. In fact, any particle, be it electron, proton, neutron, meson, or any other, in a particular situation, will have associated with it a wave function. This function does describe the observable properties of the particle, which in this case applies to electron, such as its position, energy, momentum, and so on. Let us talk about the position of the electron. Let electron's position coordinates be x, y, z. Then psi is a function of x, y, and z. So we write it as psi within brackets x, y, z, which may be rare or complex. Modulus psi within brackets x, y, z square dx, dy, dz is the probability that the electron in question would be found in a small box of sides of length dx, dy, and dz. It is possible to calculate the probability as a percentage that a particle will be in a particular place at a particular time. However, it's not always possible to get exact information about the behavior of the members of such a small system as an atom. Using the wave function, one is able to say that an electron spends a certain fraction of its time in one region and some other fraction of its time somewhere else. Figure 22.3ab shows shapes of electron clouds for s and p electrons. If one does large number of determinations of the positions of the electron, one can at best say that the fractional number of times that one could find the electron in a particular position will become closer and closer to modulus of psi xyz square as the total number of times that one performs the experiment is increased. One interprets as imagining the electron as being like a cloud of electric charge, the density of the cloud at the point xyz being determined by modulus of psi within brackets xyz square. Also, the shape of the electron cloud is different for different electrons within the atom. For example, for an s electron, the charge cloud is spherical in shape, whereas for a p electron, its shape is totally different, as shown in figures 22.3a and b. The p-type charge clouds are also sometimes named as p-type atomic orbitals, have a tendency to form highly directed bonds between two atoms. It could be that two electrons may be in each of these atomic orbitals, provided these two electrons are with opposite spins, but the Pauli exclusion principle does not permit higher population of the orbitals. How it is then that we have 6 p electrons in an atom, say like an E? It becomes possible on account of the fact that there are 3 distinct p-type orbitals in an atom, one of them directed along the x-axis as is shown in figure 22.3b. There is also a possibility to have p-type orbitals directed along the other remaining axes, that is the y and z axes. In this way, there are in all 3 p-type orbitals which together have the capacity to accommodate a total of 6 electrons. Now, if it be considered that two atoms are placed near together, there exists a possibility for the electrons' charge clouds to rearrange themselves so that at least one of these clouds embraces both the atoms, and as a result, usually taking one electron from each of the two atoms, develops a bond that holds the two atoms together in a molecule. We may extend this argument by considering in a similar way that when a large number of atoms are placed together to form a solid, these charge clouds may arrange themselves in order that any two neighboring atoms are held together by a charge cloud which goes around them both. In this process, the whole solid is held together, the bonds being covalent bonds, and the substance is named as covalent solid. Now let us take up what binds the ionic crystals to be held together. What are those forces which hold the constituents of ionic crystal together? In case of ionic crystals, it is said that starting from neutral atoms, some of these atoms lose one or more of their electrons, making them positively charged, while the other atoms guard these electrons and in the process become negatively charged. So the crystal is then held together mainly by electrostatic forces. On the other hand, in the covalent solid, neighboring atoms share some of their electrons with each other and they all remain electrically neutral. In practice, real crystals are seldom purely ionic with no sharing of electrons and with complete transfer of electrons from atoms of one kind to the atoms of the other kind. They are also not purely covalent with complete sharing of electrons between atoms and no electrical charge at all on any of the ions. If the crystal is perfect ionic, it has no directional bonds at all in it, and the perfect covalent crystal has no electrical charge on any of its atoms. However, in practice, there is no crystal which is perfectly of either type. Even a crystal like NaCl, which is generally known as an ionic crystal, can be shown to have its ions partially distorted and tend to form directed bonds between two adjacent ions. In fact, there are several structures which are covalent but do have some small positive and negative charges developing on the atoms composing the structure. Diamond is a very popular covalent bonded crystal. We do meet some examples of a mixture of ionic and covalent bonding. Some of the atoms are bound together by covalent bonds and form a large ion, and these ions are held together to build up an ionic crystal. We may take the example of calcium carbonate, that is CaCO3. The C and O atoms are held together largely by covalent bonds to make up the carbonate ion CO3 negative, and then these carbonate ions and the Ca2 plus ions are held together by electrostatic forces to build up an ionic crystal. Metallic bond. Metals are characterized by such distinctive properties such as high electrical and thermal conductivities, malleability, ductility, opaqueness, and so on. The bond which binds the atoms in metals, is typical of this group and is known as metallic bond. What holds a metal together? Since metals are characterized by high conductivity, both electrical and thermal, it is just usual as being due to free or almost free electrons within the metal. That is, a metal consists of positive ion embedded in a sea of free or almost free electrons. The metal is thought of as being held together by the electrostatic interactions between the ions and these electrons. The electrons available to participate in the conductivity are called conduction electrons. Also, part of the bonding is due to what are called exchange interactions among the conduction electrons in a metal. The term of exchange interactions appears in quantum mechanics, which treats electrons as being identical particles. Quantum mechanical treatment gives an extra contribution to the energy of the electrons in the metal, and this energy is called as exchange energy. In fact, it is exchange interactions which lead to the explanation of ferromagnetism of iron or steel. The exchange interactions between the electrons of neighboring atoms is the cause behind their preference to get lined up parallel to each other. To explain the forces which hold a metal together is rather difficult and involves many quantum mechanical concepts. Detailed discussion of these concepts is beyond the scope of this section, which may be found in references like The Wave Mechanics of Electrons in Metals by S. Reims, North Holland publication, Amsterdam. In some metals, such as the alkali metal, the interaction of the ion cores with the conduction electrons is believed to be largely responsible for the binding energy. One may think of an alkali metal crystal as an array of positive ions embedded in a more or less uniform sea of negative charge. In some metals, such as the transition metals, it is suggested that there may also be binding effects from covalent type bonds among the inner electron shells. Transition group elements have incomplete d electron shells and are characterized by high binding energy. The binding energy of an alkali metal crystal is much less as compared to that of an alkali halide crystal. As such, the bond formed by a quasi-free conduction electron is rather weak. It is partly explained to be due to large interatomic distances in alkali metals on account of the fact that the kinetic energy of the conduction electrons favors large interatomic distances, which lead to weak binding. In the transition metals, such as iron and tungsten, the inner electronic shells contribute substantially to the binding. The binding energy of tungsten, as for example, being 210 kilocalories per mole. As said above, it is rather difficult to give unquestionable explanation of bonding in metals based on classical concepts. The answer to the problem lies in considering quantum mechanical concepts. Metallic bond may be explained by free electron theory. Here the metal atoms let their valence electrons get loose and move throughout the volume of the crystal in a manner the gas molecules move in gas within a container. So the term electron gas or electron cloud is used for the free electrons in a metal. It is the attraction between the positively charged metal ions and the negatively charged electron gas that binds the atoms together to form the metal crystal. This picture, which is more of ionic nature, does explain satisfactorily several of the properties of metals, but it fails to account for the observed specific heat of metals, the theoretically predicted value being 50% higher than the observed value. A relatively more recent picture is based on quantum mechanics. Metals are electron-deficient substances, that is, the number of valence electrons is less than the number of orbitals. Modern picture of metallic bond is to consider it to be more of a covalent bond than of an ionic type, and is referred to as electron-deficient covalent bond. It may be made clear by taking an example of sodium having configuration 1s2, 2s2, 2p6, 3s. It has one unpaired electron 3s in the outer shell. This unpaired electron pairs up with that of another sodium atom. As the third unpaired electron of another Na atom approaches this pair, it gets repelled because the Pauli exclusion principle does not permit an S state to accommodate more than 2 electrons. The energy of 3s state being very close to 3p, this electron goes to 3p state. The central sodium atom with only one unpaired electron may thus form covalent bond with a number of surrounding sodium atoms. In practice, therefore, the sodium atom makes a fraction of electron pair bond with each surrounding atom. So as such, we may treat this as an electron deficient bond. Considering metal an array of positive ions and a cloud of free electrons forming some kind of gluing effect of holding the metal together, Drude somewhere in the year 1900 treated these electrons as a classical gas. It was later modified by Sommerfeld, who treated these electrons as quantum mechanical particles. Molecular bond. Molecular crystals are the solids formed by inactive atoms, such as the rare gases, and saturated molecules like hydrogen and methane. They are characterized by low boiling and melting points, and they generally evaporate in the form of stable molecules. We have discussed ionic and covalent crystals. It was also explained that how some crystals may be bound together by a mixture of these two types of bond. A molecular crystal is one more example of a crystal in which there are several different types of bond present. In ionic crystals, there is nothing that exists as individual molecule, whereas a molecular crystal is a collection of individual molecules. The atoms that compose the molecule are held together by ordinary chemical bonds, ionic bonds, or covalent bonds. Usually, molecular crystals are formed by organic chemical compounds. Obviously, the question arises as to what holds these molecules together to form crystalline solids. Most of it is van der Waals forces and hydrogen bonds, but some small amount of ionic or covalent bonding may be existing. It means that if various parts of the molecule develop small positive or negative charges, electrostatic forces between the neighboring molecules in a molecular solid will exist, which may contribute to holding the molecules together. Inert gas atoms and saturated molecules are bound together in a solid phase by weak electrostatic forces known as van der Waals forces. Van der Waals forces are like ionic forces, electrical in origin. However, their origin is different. Ordinary ionic bonds arise because of the forces between single charges. The van der Waals forces arise as a result of interaction of electric dipoles. If the dipoles formed are weak and temporary, the resultant bond is called a van der Waals bond. This type of weak force which bonds atoms was first discovered in gas atoms by van der Waals. The van der Waals bond is responsible for binding atoms in crystals of inert gases such as argon, krypton, neon, and xenon, which crystallize at very low temperatures. An electron dipole, which is a combination of two equal and opposite charges located at some fixed distance, say small d, apart, does not carry any net electric charge, but the electrostatic force of interaction between it and another electron dipole or even just an ordinary single charge does not disappear. One can judge the situation from figure 22.4 and the actual force in this case of repulsion between the dipoles can be calculated. Suppose now we reverse the direction of one of the dipoles in figure 22.4, then what happens? In that case, the net force between the two dipoles shall be of attractive type instead of repulsive type. Maybe a molecule has a permanent dipole moment, but there is still a possibility of having van der Waals forces between molecules without a permanent dipole moment. These forces arise in the following way. Even an atom or molecule which has on the average an electric dipole moment of 0, there will be a fluctuating dipole moment associated with the instantaneous position of the electrons in the atom. The instantaneous electric field associated with the moment will induce a dipole moment in neighboring atoms. The average interaction of the original moment and the induced moment result in an attractive force between the atoms. Forces of this origin are also called dispersion forces. Many organic solids are held together by van der Waals forces. An atom or molecule which has no permanent dipole moment will still have fluctuating dipole moment. What is the cause of these fluctuating dipole moments? Actually, the electrons within the atom or molecule are in constant motion, so that at any given instant, the centers of their charge distribution will not necessarily coincide with the positive charge of the nucleus. There is therefore a dipole moment which will be changing its direction and magnitude continuously. Even if the charge value of the dipole moment may be 0, on account of the fluctuations, it can be shown that the average value of force between two neighboring molecules with these fluctuating dipole moments does not come out in general to be 0. Further, it can also be shown that it is a force of attraction proportional to 1 by r raised to power 6 as is required of van der Waals forces. Molecular crystals are characterized by weak binding with low melting and boiling points. The crystal structures are often those with dense packing. The inert gas crystals crystallize with cubic close packing. Figure 22.4 shows an electric dipole. Hydrogen bond. As neutral hydrogen has only one electron, it should form a covalent bond with only one other atom. It is known, however, that under certain conditions, an atom of hydrogen is attracted by rather stronger forces to two atoms, thus forming what is called as hydrogen bond between them, with bond energy of about 5 kcals per mole. Hydrogen bond may be visualized as a directional ionic bond. Though hydrogen atom has one electron, it may under favorable conditions be attracted to other atoms, and the bond thus formed is known as hydrogen bond. Hydrogen atom with only one unpaired electron cannot form more than one pure covalent bond. Figure 22.5 and 22.6 shows formation of hydrogen bonds. Obviously, the question arises as to how hydrogen atom can form bonds between two other atoms. A simplified mechanism of this is that the hydrogen atom shares its only valence electron with another atom, and the bare proton left is attracted to the outer unshared electrons of the other atom. The formation of hydrogen bond thus appears to be due largely to ionic forces. Now let us take the example of water molecules. Molecule of water, that is H2O, may be visualized as being formed between an O and two H atoms by covalent bond, and the association of water molecules by hydrogen bonds as illustrated in figures 22.5 and 22.6. The hydrogen bond plays a very important role both in solids and liquids because of the small energy involved in its formation and rupture. The stability of protein chains by hydrogen bonds is a typical example. The hydrogen bond is an important interaction between H2O molecules and is responsible, together with the electrostatic attraction of electric dipole moments, for the striking physical properties of water and ice. The hydrogen bond restrains protein molecules to their normal geometrical arrangements. It is also responsible for the polymerization of hydrogen fluoride and formic acid. It is important in certain ferroelectric crystals such as potassium dihydrogen phosphate. The hydrogen bond plays a major role in the bonding of atoms in protein molecules as it holds these molecules to their normal geometrical arrangements. The hydrogen bond also plays an important role in atomic bondings in the molecules responsible for life processes, as for example, it controls the pairing between the two strands of a DNA molecule. Lattice energy of ionic crystals. Crystals grow in a number of ways. Several materials can be grown as crystals in the laboratory by slowly cooling the molten material below the melting point. In these cases, the crystalline solid forms when intermolecular forces of attraction overcome thermal agitation and a condensed phase results. Heat is given off in the process, and this heat is directly related to what is known as cohesive energy of the solid. The cohesive energy is a negative quantity as usually defined, and it arises largely from the forces which hold the atoms of the solid together. One of the important and fundamental problems in the theory of crystallography of solids is the calculation of the binding energy of a crystal. This cannot be done unless we have knowledge of the forces between the composing particles. The simplest group of crystals to deal with in this respect are the ionic crystals, for which calculation of the cohesive energy were made in 1910 by Born and Madelung. Since the atoms composing a crystalline solid are arranged in a regular periodic lattice, the energy responsible for binding them together is known as lattice energy or crystal energy. Lattice energy plays a preeminent role in crystallography, solid-state physics, and materials science in general. Because of their simple nature and of the applicability of relatively simple mathematical treatment, the lattice energy of ionic crystals has been the subject matter of much theoretical calculation by many workers, namely Madelung, Born, Ewald, and Eugen, etc. In the calculation of lattice energy, we shall have to make certain assumptions which are given as follows. Number one, ionic crystals are made up of positive and negative ions, the charge distribution of which is 159 spherically symmetric. In other words, the force between two such ions depends only on their distance apart and is independent of direction. This is a good example of the simplification of a problem resulting from considering certain groups of elementary particles as units, the calculation being carried out for these units rather than for elementary particles themselves. For example, in sodium chloride, it is assumed that these units are the sodium plus ion with an electron configuration 1s2, 2s2, 2p6 and the Cl negative ion with an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. In the theory, one works with these ions as charged particles, forgetting to a large extent about their internal constitution. The influence of the latter is, however, introduced in the form of refinements later. Number two, all these ions are located at proper lattice sites, as it should be in a perfect crystal. It may, however, be noted that perfect crystals do not exist, and even if a crystal is perfectly grown and chemically pure, there are always a relatively small number of lattice defects present. Interacting forces. The interacting forces which might contribute to the lattice energy of crystals are: number one, attractive force due to Coulomb interaction between positive and negative ions. Number two, attraction due to polarization of individual ions in the field of other ions. Number 3, short-range repulsive force due to overlapping of the electron density of the ions. This force comes into play when the ions come closer than the closest distance for Coulomb attraction. The main interaction, according to the theory, is the ordinary electrostatic or Coulomb force between the ions, as mentioned in the first one given above, which accounts for the large cohesive energies of the crystals. The electrostatic forces, which tend to contract the dimensions of the crystal, are balanced by repulsive forces which, from the classical viewpoint, have uncertain origin and which vary much more rapidly with increasing distance than do the Coulomb force between the charges. Number 4, van der Waals interactions between the ions. In actual calculation, however, contributions from forces given under 1 and 2 are taken into account, whereas those under 3 and 4, being very small in comparison to the former, are neglected. Let us see how far the calculated result, based on the above-mentioned assumptions and contributions, agree with the experimental results in the ionic crystal NaCl. Sodium chloride crystallizes in the structure as already described earlier in the text. The space lattice is face-centered cubic and Na plus Cl negative ions arrange alternately at the lattice points. We construct the sodium chloride crystal structure by arranging alternately Na plus and Cl negative ions at the lattice points of a simple cubic crystal. In the crystal, each ion is surrounded by 6 nearest neighbors of the opposite charge and 12 next nearest neighbors of the same charge as the reference ion. We suppose that the sodium plus ion carries a single positive charge, so that the electronic configuration is identical with neon, and the Cl negative ion carries a single negative charge, argon configuration. Taking any sodium plus ion inside the crystal as the reference point, it will have 6 ions of opposite sign, Cl negative, as the nearest neighbor at a distance, say r. Second, 12 ions of the same sign, that is Na plus, as the second nearest neighbor at a distance under root 2 r. 3, 8 ions of opposite sign, again Cl negative, at a distance under root 3 r. 4, 24 ions of opposite sign, that is Cl negative ions, at a distance under root 5 r, and so on. This ion will attract or repel one another, as the case may be, by Coulomb interaction. The electrostatic energy of the sodium plus ions with each of the surrounding ions can be written by following the method developed for ion pair. Sodium and chlorine ions have obtained the configurations of the nearest inert gas. Sodium ion having the configuration of neon and the chlorine ion that of argon. The bonding is as a result of a Coulomb-type attraction between the positive and negative ions. Taking a general case, the force of attraction F subscript A between the ions is given by Coulomb's law, Fa equal to plus Z1e into minus Z2e upon r square, where Z subscript 1 and Z subscript 2 are the ionic charges. Small e is the electronic charge and small r is the distance between the ions. Therefore, the electrostatic energy of the Na plus ions with each of the surrounding ions may be given as E attraction equal to epsilon subscript E into 6e square upon under root 1r plus Z1 into minus Z2 plus within brackets 12e square upon under root 2 dot r into plus within brackets Z1 square plus within brackets 8e square over under root 3r within brackets plus Z1 into minus Z2 within brackets plus within brackets 6e square by 2r into within brackets plus Z1 square plus within brackets 24e square upon under root 5r plus within brackets Z1 into within brackets minus Z2 plus dash 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 etc. In the present example of NaCl, the two ions carry equal but opposite charges and hence plus within brackets Z1 is equal to minus within brackets minus Z2 or Z1 is equal to Z2 is equal to modulus Z. E attraction is equal to epsilon subscript E equal to minus E square modulus Z square upon R into within brackets 6 over under root 1 minus 12 over under root 2 plus 8 over under root 3 minus 6 over under root 4 plus 24 over under root 5 plus minus etc. etc. The series within the bracket depends purely on the type and structure of the crystal. The term within brackets is called the Madelung constant and represents the geometrical arrangement of ions. It can be seen that the convergence of this series is poor. It was first calculated by Madelung and so is called Madelung constant capital A. Small e is the charge per ion and small r is the shortest interionic distance. It may be noted that because Coulomb force is decreased relatively slowly with distance, it is not sufficient to consider only a few shells of ions around the central ion. Evidently, the coefficient E square upon R is a pure number determined only by the crystal structure. Series of this type have been calculated by Madelung, Ewald, and Eugen. For the NaCl, the result is epsilon subscript E equal to minus capital A E square upon R with capital A equal to 1.747568. For other crystal structures composed of positive and negative ions of the same valency, the Madelung constant R, cesium chloride, that is CsCl, A equal to 1.762670, zinc blend, that is ZnS, A is equal to 1.6381, verticide, that is zinc sulfide, ZnS, A equal to 1.641. It may be noted that small a in the above equation represents in general the electronic charge times the valence of the ions under consideration. The minus sign in equation number 22.2 indicates that the average influence of all other ions on the one under consideration is of attractive nature. To prevent the lattice from collapsing, there must also be repulsive forces between the ions. These repulsive forces become noticeable when the electron shells of neighboring ions begin to overlap, and they increase strongly in this region with decreasing value of R. These forces, as other overlap forces, can best be described on the basis of wave mechanics on account of the fact that they are of non-classical nature. Born in his early work assumed that the repulsive energy between two ions as function of their separation could be expressed by a power law of the type capital B by R raised to n. It may be expressed as exponential REP, that's exponential repulsion, is equal to capital B by R raised to n, which is represented as equation 22.3. It suggests that the repulsive force has been assumed to be inversely proportional to some power of the distance of separation between ions represented by small r. Capital B represents a constant and small n is a number known as Born exponent. Both capital B and small n are characteristic of the ions in the solid under consideration. Equation at number 22.3 is an expression for the repulsive energy of one particular ion due to presence of all other ions. The repulsive term in the case of NaCl is written as epsilon repulsive equal to capital B upon R raised to n. In view of the fact the repulsive forces depend so strongly on the distance between the particles, the repulsive energy, that is epsilon Rep, is mainly determined by the nearest neighbors of the central ion. Thus the total energy, that is the potential energy of one ion due to the presence of all others, is then obtained by adding equation at 22.2 and 22.3. Epsilon is equal to minus capital A E square upon R plus capital B upon R raised to power small n, given as equation 22.4. Assuming that the two types of forces just discussed above are the only forces involved in the subject matter under discussion, we have to take into account and neglecting the surface effects and proceed further in the determination of total binding energy of a crystal containing capital N positive and capital N negative ions. Capital E subscript within brackets small r equal to capital N within brackets minus capital A E square upon R plus capital B by R raised to N is equal to N epsilon subscript within brackets small r, which is given as equation 22.5. It may be noted that we have multiplied by capital N rather than 2 capital N, because otherwise the energy between each pair of ions in the crystal would have been counted twice. The two contributions to the total binding energy ER are represented schematically in the figure. The figure is a schematic representation of the energy of attraction 1 and of represented as 2 as a function of the lattice parameter. The resultant, that is represented by 3, exhibit minimum for a lattice constant or O corresponding to equilibrium. The figure shows dependence of potential energy of ionic crystal on the value of lattice constant. Considering the crystal at absolute zero, the equilibrium conditions require that the potential energy capital E should be minimum, which will be the case for the equilibrium when R is equal to R0. That is the equilibrium distance, where R0 represents the smallest interionic distance in the crystal at T equal to 0. The equilibrium distance R0 can be obtained by differentiating equation number 22.5 with respect to small r and equating it to 0. That is the attractive force being balanced by the repulsive force at the distance. That is dE upon dr at r equal to r0 is equal to 0. So, or we can say dE by dr at r equal to r0 is equal to capital A into small e square upon r0 square minus small n into capital V upon r0 raised to n plus 1 is equal to 0, given as equation 22.6. R0 comes out to be equal to n small n into capital B upon capital A into e square raised to 1 upon n minus 1, given as equation 22.7. We get from equation number 22.6 RO equal to capital A E square upon n into R0 raised to n minus 1. That's equation 22.8. Substituting it in equation number 22.5 yields for the lattice energy E subscript capital L is equal to E within brackets R0 is equal to n into within curly brackets minus capital A E square upon R0 plus capital A E square upon small n into R0 raised to n minus 1 dot 1 upon R0 raised to n, which is equal to minus n capital A E square upon R0 into 1 minus 1 upon n, which will be equal to capital N into epsilon subscript capital L. That is given as equation 22.9. The interionic distance can be obtained from X-ray diffraction data. The charge per ion is also known, and thus the lattice energy can be calculated if the repulsive exponent small n is known. The question now remains how to determine small n. The discussion on that will follow now. That is the calculation of repulsive exponent. Repulsive exponent can be calculated from compressibility data. Born obtained the unknown repulsive exponent small n from measurements of the compressibility of the crystal as follows. The compressibility represented by capital K is defined as capital K equal to minus 1 upon V within brackets into dV by dP, given as equation 22.10. At very low temperatures, we may neglect thermal effects, and using first law of thermodynamics, expressing the equation as dE is equal to minus P dV, minus dE upon dV is equal to P, or minus d by dV into dE upon dV is equal to dP by dV. Therefore, minus d2E upon dV2 is equal to dP by dV, given as equation 22.11. From equation number 22.10, we have 1 upon capital K equal to minus V dP upon dV, where V0 is the volume of crystal corresponding to an interionic distance R0. V corresponds to the variable R. Now the relation between volume and interionic distance must of course be of the form V is proportional to nR cube, so that V is equal to C into N into R cube, given as equation 22.13, where capital N is the total number of molecules, small r is the nearest neighbor distance or interionic distance, capital C is a constant and is characteristic of the type of lattice. For NaCl, as per example, C is equal to 2. Now dE upon dV is equal to dE upon dr into dr upon dV, given as equation 22.14. From equation number 22.13, we have r cube equal to V upon Cn. So 3r square dr is equal to 1 upon C into N into dV, or dr by dV will be given by 1 upon 3r square Cn. This is 22.15 equation number. Substituting it in equation number 22.14, we may write dE upon dV is equal to 1 upon 3r square C into N into dE upon dr, or d2E upon dV is 2 is equal to d upon dV into 1 upon 3r square Cn into dE upon dr, which comes out to be equal to 1 upon 3 Cn into d upon dV of 1 upon r square dE upon dr, which is equal to 1 upon 3 Cn dr by dV into d by dr into 1 upon r square into dE by dr. Substituting for dr by dV from equation number 22.15, we have, where capital N is the total number of molecules, small r is the nearest neighbor distance or interionic distance, capital C is a constant and is characteristic of the type of lattice. Substituting for dP by dV from equation number 22.11, we have 1 upon K is equal to V dot d2E upon dV2. At absolute zero, we represent for K as K0 and V as V0. Therefore, 1 upon K0 is given by V0 into d2E upon dV2 at V equal to V0, or 1 upon K0 V0 is equal to d2E upon dV2 V equal to V0, given as equation 22.12, where V0 is the volume of the crystal corresponding to an interionic distance R0, V corresponds to the variable R. Now the relation between volume and interionic distance must of course be of the form V proportional to nr cube, or V is equal to C n r cube, given as equation 22.13, where n is the total number of molecules, r is the nearest neighbor distance or interionic distance, c is a constant and is characteristic of the type of lattice. d2e upon dv2 is equal to 1 upon 3 cn into 1 upon 3 r square cn into, within curly brackets, d by dr of 1 upon r square de upon dr, or d2e by dv2 is equal to 1 upon 9 c square n square r square d by dr of 1 up square dot de by dr, which is given as equation 22.16. From equation number 22.5, we have d by dr is equal to n within brackets plus ae square upon r square minus nb upon r raised to power n plus 1. Substituting for d by dr in equation number 22.16, we have d2e by dv2 1 upon 9c square n square r square d by dr of 1 upon r square capital N a e square upon r square minus capital N small n b upon r raised to n plus 1 bracket close is equal to 1 upon 9 c square capital N square r square d upon dr of n a e square by r 4 minus n into small n capital B upon r raised to n plus 3, which comes out to be equal to 1 upon 9c square n square r square into minus 4 capital N capital A into e square upon r into r 5 plus n into n plus 3 capital B upon r raised to n plus 4. Substituting for d upon dr in equation number 22.16, we have d2e upon dv2 equal to 1 upon 9c square n square r square d by dr of 1 upon r square into nae square upon r square minus nb upon r raised to n plus 1, which comes out to be equal to 1 upon 9c square capital N square r square d by dr of nae square upon r4 minus n capital B upon r raised to n plus 3, which is equal to 1 upon nc square n square r square into minus n minus 4 n a e square upon r5 plus n upon into n plus 3 up to b upon r raised to n plus 4. Now at r equal to r0 and using equation number 22.12, we have 1 upon k0 v0 is equal d2e upon dv2 into at r0, which is equal to 1 upon 9c square n r0 square into minus 4 ae square upon r0 raised to 5 plus small n into small n plus 3 capital B upon r0 raised to n plus 4. Using equation 22.13 for v equal to v0 and making substitution for capital B from equation 22.8, we get 1 upon k0 c n r cube equal to 1 upon 9c square capital N r0 square into bracket minus 4a e square upon r0 5 plus n into n plus 3 a e square r0 n minus 1 upon n into r0 n plus 4 bracket close. 1 upon k0 r0 is equal to a e square upon 9c into minus 4 by r0 5 plus n plus 3 upon r0 5, which is equal to capital A into e square upon 9c r0 5 into n minus 1, or 1 upon k0 r0 plus ae square upon 9c r0 5 is equal to n into ae square upon 9c r0 raised to 5, or n is equal to 9c r0 4 upon k0 ae square plus 1, which is given as equation 22.7. Now for NaCl, this factor C is equal to 2. So N is equal to 18R04 upon K0 AE square plus 1, which is given here as equation 22.18. From equation number 22.17, the parameter small n can be calculated if K naught is known. For example, the compressibility of sodium chloride as measured by Slater is 9.4. There are some small variations in the value of small n as measured by different workers. However, in general, values of small n computed from equation number 22.17 are as low as small n equal to 6 for lithium fluoride, small n is equal to 10 for NaCl, small n is equal to 10.5 for CCCl, and as high as small n equal to 11 for RBI. An improvement in the theory of cohesive energy is made by introducing van der Waals, that is dipole-dipole interactions, as well as vibrational energy. An approximate value of 0-point lattice vibrational energy per ion pair can be obtained by making a Debye approximation and using a characteristic cutoff frequency nu-m. The relative importance of the Coulomb repulsive, van der Waals, and 0-point terms for three materials of NaCl structure are given in Table 22.1. Table 22.1 provides various contributions to the binding or cohesive energy of some ionic crystals. Now, the type of force, the expression used, the crystal, that sodium chloride, RBI, and AgBr, silver bromide. The type of force, Coulomb, expression is minus capital A E square upon R. The crystal is NaCl, minus 8.85 electron volt. RBI is minus 6.79 electron volt. AgBr has minus 8.65 electron volt. Now the type of repulsive force, expression B upon twice Rn. For NaCl it is 1.02, for RBI 0.67, for AgBr 1.37. Now the type of van der Waals forces, the expression capital C upon R raised to power 6, for NaCl minus 0.125, for RBI minus 0.175, for AgBr it is minus 1.18. 0 point expression is 9 by 4 H into nu subscript m. For NaCl it is 0.075, for RBI 0.0312, for AgBr 0.0375. The total for NaCl is minus 7.90, for RBI it is minus 6.26, for AgBr it is minus 8.4. These values are based on N.F. Mott and R.W. Gurney, that is the electronic processes in ionic crystals, published by Oxford University Press, New York, 1948, and also M. Born and M. Gopert Mayer, Handbuch der Physik 24 by 2, 726, published in 1933, and also Z. Physik 75, 1, 1932. Theoretical and experimental lattice energies. The lattice energy E subscript capital L may be calculated from equation number 22.9 on substitution by the proper values for the charge of the ions, the interatomic distance, and Born exponent small n. One can see from the expression that the lattice energy is smaller than Coulomb energy by 1 upon small n. The repulsive potential exponent or the Born exponent small n can be calculated from the compressibility data of crystals. Its value has been found to be in the neighborhood of 10 in most of the ionic crystals. The lattice energy of NaCl, calculated from equation number 22.9, has been found to be 8 electron volt, whereas the experimental value is 7.9 electron volt. It is a reasonably good agreement between theoretically calculated and the experimentally measured values of lattice energy, which is also known as cohesive energy of ionic solids. The agreement could be more convincing when contribution due to other forces of interaction, that is van der Waals forces, are taken into account in addition to those given in equation number 22.4. Let us now summarize of what we have discussed so far. Binding forces that hold a crystalline solid together are described. Classification of solids according to the type of bonding in them is discussed. Different types of bonding, namely ionic, covalent, metallic, molecular, and hydrogen bonds in crystals are discussed, providing an understanding of how crystalline solids are held together. Interacting forces that contribute to the lattice energy of crystals are described. Expression leading to determination of lattice energy of ionic crystals is derived. Calculation of repulsive exponent from compressibility data is explained. The validity of expressions obtained on lattice energy is shown to get support by agreement of theoretical and experimental values of lattice energy of a crystal.